Hi, my name is JooYeong Kim, and I'm glad to share our work, Visual Nuances, a caption system to visualize paralinguistic speech cues for deaf and hard of hearing individuals. In the speech, nuance completes the speaker's real intention. As the example shows, the meaning changes depending on which word you emphasize. However, since captions only express the literal content, these meanings created by sound become ambiguous. Hearing people can directly capture the nuance with sound, but deaf and hard of hearing people don't, so they often rely on facial expressions or context along with captions. The purpose of this work is to visualize sound elements using caption elements, helping deaf and hard of hearing viewers easily access nuance information through captions. We propose an audio-visualized caption system. Inputs are an audio file and a caption list. First, a vocal sample is extracted from the mixed audio channel using a pre-trained source separations model. Second, the extracted vocal sample is segmented into caption units based on the start and end time of the corresponding caption. The emotion classifier recognizes the emotional nuance of the caption unit speech. Meanwhile, caption unit samples are segmented into syllable units to calculate the volume and pitch values of syllable unit speech. The analyzed sound features are mapped to the corresponding caption element according to caption style mapping rules. And finally, we can get a single line of audio-visualized caption. As the first step in designing the system, we had to select the caption elements that best represent each sound feature. So we surveyed 20 hearing college students and counted the votes on the most suitable caption elements for volume, pitch, and tone. And based on those top-ranked elements, we decided to map the speaker's volume to thickness, pitch to height, and tone to motion and font. Next, we designed the mapping set of sound caption elements. Let's start with tone. Through a design workshop, we defined the font and motion styles that best represent emotional and emphasized tones. When applied by our system, if the speech is recognized as angry tone by the classifier, the pair of angry is applied to the caption unit. To process volume and pitch, each syllable's volume is mapped into one of four levels in CSS font weight property, and pitch is normalized from 0 to 5 pixels, which expresses the pitch height by lifting the text height from the baseline. So there's no sound in the video here, but you can see how he is speaking through the caption. To investigate the effectiveness of audio-visualized captions, we conducted a comparative study of 3 caption systems. Basic captions express only volume and pitch, but advanced captions include font and motion to provide more nuanced expression. In this study, 20 deaf and hard of hearing people were recruited. Most of them lost their hearing at an early age, and they were highly caption dependent and enjoyed watching videos. As video materials, 2 video categories were used, formal talk and drama, and 2 samples were prepared for each category. For the measurement, we evaluated task performance, speech accessibility and experience, and legibility and cognitive load about captions. First, I want to show whether our participants can identify the nuance through our captions. As you can see, task performance results show that our captions improved more accurate and nuanced identification. Especially in formal talks, the rate of don't know significantly dropped from 35% to 7.5%. It means audio-visualized captions worked better in formal talks with little change in visual appearance. We also observed small improvements in dramas, and one interesting point is that some participants selected more detailed emotion word while answering task questions. In the subjective questionnaire, participants responded they could feel paralinguistic speech cues more clearly and naturally through the audio-visualized caption. However, participants generally experience lower legibility and higher cognitive load from the audio-visualized captions. These results might be natural because they were unfamiliar with such a new caption style like basic or advanced. Some participants expressed confusion due to visual fatigue while reading audio-visualized captions. Interestingly, in formal talk videos, we observed higher legibility and lower cognitive load in advanced caption than common captions. It's supposed that motion of advanced captions presented more intuitive cue on which part was being emphasized in a monotonous formal talk. When compared with the result of hearing participants, we found that deaf and hard of hearing participants experienced a similar level of sound accessibility to hearing participants. However, limitations still exist in achieving the same level of accessibility as hearing people. During focus group interview, deaf and hard of hearing participants reported they need time to adapt to audio-visualized captions because they had rarely experienced the concept of the sound nuances. This highlights the need for future work to provide training on this system and improve their understanding of universal nuances. In the discussion section, we discuss possible design implications for future work. For more details on implications, please refer to our paper. In summary, this work demonstrates that audio-visualized captions can convey the nuance of speech to deaf and hard of hearing individuals, even those who have never experienced sound. Also, the proposed caption system showed more effectiveness in formal talk video, where the speaker's facial expressions were less evocative in capturing the nuances. We present design improvements for future works. Particularly, future work have to focus on legibility and provide sufficient time for acclimation. And in closing, if the caption system can be improved based on the insight from our work, we believe that audio-visualized captions will provide deaf and hard of hearing viewers with a more accessible and enjoyable video watching experience.